Hello everyone. So, today we will start the combined heat and mass transmission and its relation with clothing comfort. Till now what we have discussed, the heat transmission and moisture, vapor and liquid transmission separately, and it is very important to know their transmission characteristics through clothing to understand the comfort. Okay. But today we will discuss few phenomena, those who are interlinked. Actually heat and mass transmissions are interlinked phenomena. So, these are the dynamic state condition. In dynamic state, what we will see that the heat and moisture transmission takes place together, we cannot separate out, and the clothing comfort like heat transmission, warm feeling and cool feeling, those are actually related to the dynamic state, because our most of the cases when we move, when our body posture changes, though the heat and mass transmission cannot take place in static condition, steady state condition, those are in dynamic condition. We will discuss the issues related to dynamic transmission. Then the transmission in hygroscopic material. Basically hygroscopic material, most of the hygroscopic material after absorption of moisture, they release heat. So, the moisture transmission or absorption and heat are interlinked. So, this phenomena we will discuss how hygroscopic materials are interacting with moisture and to release the heat. Okay. This segment we will discuss, and then the buffering, temperature buffering and chilling aspects, they are related with the heat and mass transmission. The moisture absorption, that is and then it sometime it causes a chilling, that discomfort related to chilling, this we will discuss. Clothing thermal insulation during sweating. So, during sweating the clothing normally actually release heat very quickly. So, this part we will discuss. Then the comfort, discomfort related to dampness. Dampness related discomfort irrespective of the temperature, it creates our severe discomfort if the microclimate is damp. So, this are actually the dampness is related again with the heat and mass transmission. The clamminess. So, again clamminess, it is a high humidity condition, this in the microclimate, that we will discuss. Even in the atmosphere, if there is a high humidity, we sometimes feel clamminess, and in that state how the temperature or heat transmission take place and temperature rise takes place, that we will discuss. And surface temperature of clothing during high activity, this we will discuss, and this is related with the again with the moisture absorption, because most of the hygroscopic fiber are actually after absorption of heat they release heat. So, if again microclimate thickness, if it changes, the heat and mass transmission also changes, this aspect also we will discuss here. And parameters, what there are various parameters which actually are used to express heat and mass transmission together. So, till now what we have discussed, the parameters are separately which are used to express the heat transmission or mass transmission. So, here we will discuss the combined parameters, and then clothing ventilation, how the clothing ventilation affect the heat and mass transmission, these aspects we will discuss here. So, we will first start with that heat and mass transmission, the phenomena. The fabric layer is characterized by two types of resistance. One is heat resistance, another is the moisture vapor resistance, that is moisture vapor permeability. Okay. So, resistance to dry heat, that is insulation, which is actually dependent on, it increases with the increase in thickness of the enclosed air layer. This thickness of enclosed air layer, it may be within the structure or may be outside the structure. Outside the structure means it is a microclimate, okay, and within the structure means it is within the pores of the yarns or fabrics. Thickness of the fabric layer. So, higher thickness means higher entrapment or higher more materials are there. So, that will also affect the dry heat transmission. Even higher more material, more number of fibers in the cross section or across the plane, which restrict the radiative heat loss. So, that also it affects, and dryness of the material. The dry material, wet material, that means that it loses its insulation. So, its conductivity is more. So, dryness of material is also directly related with the dry heat insulation. Coming to the moisture vapor transmission, it generally more dependent on fabric parameter, but it decreases with increase in thickness of air layer. That means, the moisture vapor permeability for thicker fabric, its moisture vapor permeability will be less. There are various factors that we have already discussed in the last segment. Basically, if the micropores are larger in size, that diffusion will be slower. Okay. So, this it decreases with the increase in thickness of air layer. Now, coming to the dynamic state, in most of the conditions, most of the time the clothed human body is in dynamic state. While we are walking, we are doing activities. So, changes in environmental variables. So, our atmosphere continuously changes, its temperature, relative humidity, everything changes, even wind speed. So, that this changes in environmental condition always affect the heat and mass transmission. So, this dynamic state, it is always we apart from the standard atmosphere, standard chamber, climatic chamber or standard test chamber, normal environment is always changing, and that directly affect the heat and mass transmission. We have to understand this one. Then air enclosed within the clothing, that is in microclimate, always in under dynamic condition. Even when we are sitting, even if we move little movement, that total air enclosed air volume will change, their total structure that is the microclimate total contour will change. So, that will affect the heat and mass transmission. And forced convection. So, when we move, when we are walking, we are doing activity, so that fabric actually move around our body, and that enclosed air actually it get pumped out and fresh air comes. So, that is a forced convective movement of air takes place, okay, through the opening of the clothing, and the enclosed air transmit directly through the fabric layer to the environment. So, that also it takes place, it is most of the cases, and this air exchange reduces the insulation. So, as air, the steel air moves away, so it takes moisture, and that means moisture vapor permeability also increases due to the forced convection. So, that total dynamics will change. So, that means in most of the cases our the comfort feeling are totally different than what we try to get. We try to get the data in steel condition, okay, in standard atmospheric condition. So, this is due to the dynamic nature of this dynamic state of our clothing and our body. So, the final exchange of heat and moisture vapor is dependent on the level and pattern of activity and the size of the opening. So, if our activity is more or if it is say wind condition, the total dynamic, the heat and mass change will be different. So, wind and physical movement decrease the insulation of air sticking to the outside of the surface of the body. So, when the wind is blowing, so the still air which is just outside the clothing, that will move out. So, that will help in better forced convection. Okay. So, with the large opening in the clothing structure, the wind penetrates inside the clothing and changes the moisture, relative humidity and temperature. So, heat loss increases. So, if the opening size is more, the forced air will enter due to the wind blowing and it will decrease the temperature, that means heat loss will increase. So, in extreme conditions like in strong wind, sometime what happen, our clothing may get compressed, that means it will take out the excess still air from inside, and thus in strong wind automatically the insulation reduces. So, for if we see, so all these conditions they are totally related with the heat and mass transmission. So, if it is strong wind, there will be some effect. If it is light wind, the effect will be basically from, it will take away the still air from outside. So, if it is strong wind, it will compress the fabric. So, these things are actually changing, and this is basically we have to understand. We cannot test, we cannot actually simulate these things, but if we understand this phenomena, then we can predict the comfort characteristics. Okay. This we have discussed, and next is that again if we continue, the insulation of clothing also reduces if the clothing gets soaked with the sweat and water. So, that automatically it will reduce the thermal resistance if it is soaked, because the water, as we have discussed, the water the thermal transmission through water is very fast. It is that is resistance of air is much higher than the water. Okay. The evaporative heat dissipation from wet clothing can be significant, actually significant extent, especially when air velocity is high. Okay. This is due to forced convection. When the person comes to rest, so after heavy activity, if the person comes to rest, what will happen? He will actually stop sweating, and then the evaporative heat loss will take place. So, his heat generation is less, but heat loss will be very high. So, that is why he will feel immediately cold. So, unwanted cooling will take place. So, this we can, typical example is a soccer player when he is coming out from the field. So, he will start feeling cold because of the less activity and the evaporative heat loss. So, this dynamic heat and moisture vapor transmission characteristics of clothing cannot be expressed in a single term. So, because we have to understand that the steady state condition of heat transmission separately, moisture transmission separately, this will not work actually. Those heat and moisture vapor transmission, it is important just to understand the phenomena, but if we try to predict the clothing comfort, we have to actually think in different direction. So, and also we have to see that our body is in dynamic condition and activity level we have to understand, then we can predict the comfort state. Now, so combined heat and moisture interaction, if we try to see here, the moisture transmission through a textile material is not only associated with the mass transmission process, but the transmission of heat must also be taken into account. So, moisture transmission, if we see it is if in earlier segment we have seen the moisture transmission separately. It is not the only the moisture is getting transmitted, it is not the sweat is getting transmitted, it is not the moisture vapor is getting transmitted. Along with the moisture, heat is also transmitted. That this phenomena we have to actually understand very clearly. So, that means heat and moisture transmission in hygroscopic material is inseparable. Okay? Actually, it is they cannot be separated. If we particularly if we consider a hygroscopic material, when mass transmission takes place, the heat transmission you have to also consider, otherwise we will not be able to predict the comfort feeling. Okay. So, that is very important, we cannot separate it. So, now if we see the hygroscopic material, let us see example is cotton. So, during the transmission of water molecule through the hygroscopic material, the water molecule gets absorbed by the molecule. So, then as soon as it absorbs the moisture, it will release the heat, which is known as heat of absorption or heat of sorption. So, this phenomena after absorption it releases heat, that means automatically the moisture transmission and heat transmission comes into picture. Understanding of heat transmission and moisture transmission, we have to it is actually it is necessary to understand this phenomena. So, due to the production of heat, what happens? The temperature of the cloth increases, surface temperature of the material increases, and it affects the moisture vapor transmission also. It reduces the moisture vapor transmission. Okay. So, due to increase in the surface temperature, and with the increase in humidity. So, what happened? The heat transmission efficiency of the material increases, because the hygroscopic material absorb moisture, become wet or moisture content increases. So, thermal conductivity automatically increases. So, that is how it is interrelated. The heat transmission process also comes into play during the moisture transmission, that is what we have discussed under the dynamic conditions due to phase change of water molecule. So, one thing is that it is actually when hygroscopic material absorb moisture, it releases the heat of sorption, that you have to understand. When hygroscopic material absorb moisture, the thermal conductivity of the total fabrics, total structure increases, that we have to understand. And also another parameter is that when it actually changes its phase, that means from liquid phase to vapor phase, okay, when it gets evaporated. So, that latent heat of evaporation it takes away from the body, from the cloth. So, that we get cooled. So, this all this interlinked phenomena ultimately affect the clothing sensation. So, the coupling effect between moisture diffusion and heat transmission depends on the following properties. Because when moisture actually diffuses through fabric, so these are the factors. What are the properties on which this phenomena depends? The moisture sorption capacity of the material. So, if the moisture gets absorbed through the by the material, so that will affect the this heat and mass transmission characteristic. Let us see one polyester fabric, another is cotton fabric. In case of polyester fabric, let us assume polyester is totally hygroscopic, hydrophobic. Okay. So, that hydrophobic fiber, it is not absorbing the moisture, moisture is transmitting through the fabric structure by diffusion. Okay. So, in that case, in case of cotton on the other hand, when it absorbs moisture, it releases the heat of sorption. So, total phenomena of heat transmission will change, and after absorption of moisture, when it actually releases moisture, it gets evaporated, it it takes away the latent heat. In case of polyester it is not happening, and fiber diameter also. So, higher fiber diameter means lower specific surface area, and that means its moisture vapor permeability will change, that will ultimately affect this heat and moisture sensation. Water vapor diffusion coefficient. So, if the water vapor diffusion coefficient is high, that means the fiber will actually diffuse the moisture quickly. Okay. Density, it is depending on the density of the structure and also the fiber, and heat of sorption. So, higher heat of sorption of fiber will give warmth feeling when it absorbs moisture, like wool fiber has got very high heat of sorption. So, that means with the change in humidity level, wool gives warmth. Okay. So, the heat of wetting of cellulose fiber depends on various factors, mainly it is a crystallinity. So, it decreases proportionally with the increase in degree of crystallinity. So, that heat of sorption, if the cellulosic fiber has got higher crystallinity, its heat of sorption will reduces. Okay. Now, another phenomena which is temperature buffering and chilling. This phenomena is again linked with heat and moisture transmission of clothing. So, what is buffering? So, these two phenomena are associated with the simultaneous heat and moisture vapor transmission through fabric. There would be a buffering effect at the starting point, at the onset of the perspiration in hot climate. Okay. So, in hot climate and humid climate, the perspiration will start, and that will actually give the buffering effect. Whereas, in case of cold climate, it would result in post exercise chilling effect. So, in hot climate we will start sweating, and that will give us warmth. So, before we come out of that out to the environment, in hot environment, we will start getting hot feeling. So, it is giving a buffering effect. Okay. So, buffering effect increases, it is experienced due to the perspiration in hot climate, as we have discussed. In hot climate we actually feel that it is warmth. Sudden increase in relative humidity in the climate, fabric also absorbs moisture and generate heat. So, it releases heat. This gives rise to the thermostatic or buffering action of the person. So, before he is going out to the hot climate, the cloth also actually prepared him with the buffering effect. That means its cloth has become warm. Okay. So, that he is not suddenly getting a shock. So, it gives some buffering effect. So, we will see in opposite case also it happens. Okay. So, hygroscopic fiber absorbs moisture and release heat. So, buffering from sudden chilling. So, this phenomena we can see in extreme cold climate zone, where suppose it is a snowing. A person in a hot and dry climate at inside a room, when he is coming out, what happens? This has significant impact on the heat balance and thermal properties of wearer experiencing a sudden change from warm and dry atmosphere to cold and humid atmosphere. What happened? When as soon as he is going out, the cloth, suppose a woolen cloth he is wearing, and as soon as he is going out in cold and humid environment, the fabric absorbs, wool absorb moisture and releases sufficient quantity of the heat of sorption. That means, for some time at least that cloth is protecting him, he is not getting sudden cold shock. Okay. reduces the working performance. Okay. The chilling effect is also associated with the exercise sweating in cold climate. Okay. So, in earlier case we have seen that when he is going out, the heat is generated, and even in the cold climate, extreme cold, when it is there and it is sweating high humidity, he is feeling warm due to heat of sorption, and the chilling effect is there. That means, chilling effect means when the cloth is wet, he will actually, the body will release the heat very fast. So, it is just opposite. So, the chilling effect is associated with the after exercise sweating in cold climate. So, after, suppose after walking someone stops. So, this reduces the working performance, because he will start releasing heat at a very high rate, he will feel cold. So, it may cause hypothermia due to excessive cold. So, water vapor may get condensed and it reduces the thermal insulation. So, all these phenomena may also take place if we actually the cloth is wet due to sweating. So, that means here again we are saying that chilling effect is associated with the heat and mass transmission. In case of only if we see here the person is not sweating, that means he will not feel the chilling effect. This chilling phenomena is associated with the heat and mass transmission. Okay. When the water vapor, that is perspiration, comes into contact with the cold wall, that is the cloth, then it gets condensed and reduces the thermal sensation. That is chilling basically. So, it is related with the again heat and mass transmission. So, both this buffering and chilling are mainly dependent on atmospheric temperature and humidity condition. So, this if this changes, like atmospheric temperature is, if it is hot and if it is dry, the buffering effect will be different. If it is cold dry, it will be different. If it is cold humid, it will be different. So, this buffering and chilling it is mainly depending on the atmospheric condition, the activity of the person, the type of clothing material. So, these things are related, but effectively this buffering and chilling, they are interrelated and they are related with the heat and mass transmission. Now, next is again another phenomena, that is the thermal insulation during sweating. The clothing thermal insulation is used to determine the heat stress of the clothed person. So, if the insulation is high in hot environment, that means he will have higher heat stress. So, in hot environment and in a humid environment, it is a very difficult. Okay. It will feel totally uncomfortable. The amount of moisture vapor evaporation mainly just to maintain the thermal balance, okay, of the body. Okay. So, that the thermal balance is actually maintained by the moisture evaporation, and if the evaporation is low, that means in humid climate, in hot and humid climate, if the evaporation is low, then he will not be able to evaporate the moisture. Okay. And also it depends on the rate of sweating and skin wetness. So, this thermal clothing insulation, it drops with the rate of sweating, and if the skin is wet, again thermal insulation will drop, and the total heat transmitted through clothing is commonly considered as the sum of dry transmission and evaporative heat transmission. So, this to dry transmission means conduction, convection and radiation plus evaporative heat transmission, and evaporative heat transmission is the phenomena which is linked with the mass transmission. Okay. The thermal insulation of non-perspiring and perspiring conditions are totally different. Okay. So, the clothing thermal insulation decreases during perspiration, that we have seen, and in the as compared to non perspiring condition, it reduces 2 to 8%, and that reduction is mainly due to the conductive heat loss. Okay. Thermal, so amount of reduction varies from 2 to 8% depending on the water accumulation. If the water accumulation is high, if the person is sweating profusely, then it may go up to 8 to 10% reduction. And the heat loss greatly increase with the sweating due to evaporative heat loss also. So, it is basically the if the sweat gets evaporated, then heat loss is also increasing. Now, coming to the phenomena of dampness. So, most of the cases we feel that if it is a damp, irrespective of the temperature of the environment, we feel discomfort. It is a very common discomfort. Okay. So, moisture in clothing has been widely recognized as one of the most important factors contributing to the discomfort sensation. So, it actually main factor which contribute the discomfort sensation. The sensation of dampness is related to the amount of sweat accumulation in the microclimate, okay, and the clothing. So, it may be in the liquid form or may be in the vapor form. So, higher humidity in the microclimate or higher moisture content in the clothing will give the dampness sensation, which is very which creates a discomfort sensation. So, moisture in clothing means discomfort. So, more the hygroscopicity of the fiber, more will be the moisture gain by the fiber, and in turn the fabric, that means the fabric, if it absorbs the moisture, the fiber, the microclimate will be little bit dry, and people we will feel total comfort sensation. When the fabric is wet and it comes into contact with our skin, it drops the temperature. So, one is the sensation, the dampness sensation, another is the temperature drop due to the wet cloth, that is the chilling process. So, chilling sensation is there, and also in the dampness, the skin temperature drops increases when it is coming into contact with the wet fabric, and the temperature drop increases with the increase in hygroscopicity of the fiber. The cotton is cooler in touch at high humidity, that is basically due to the hygroscopicity of the fiber. Also, the temperature drop is influenced significantly by the degree of the fabric skin contact. Okay. So, that we have also seen in cold touch, warm touch. So, if the fabric structure is such that higher contact area, higher surface contact area is there with the skin, that same fabric will, that the fabric made of the same fiber will give higher coolness. Okay. Contact with the, like fabric made of say wool fiber. Wool fiber in high humidity gives actually the warmth in nature. So, this warm nature with the of wool fiber and cotton gives a cooler touch. There are combined factors. One is that wool is actually heat of absorption is high in case of wool, it gives automatic warmth, and also the wool fiber has got its crimp, natural crimp, very high crimp. So, that result less contact area. So, that gives the wool fiber, fabric made of wool is naturally its warmth, even if it is the high humidity condition. Now, dampness, that in ambient condition such as temperature and relative humidity influence the skin temperature drop significantly. So, if the ambient temperature is high, what will happen, and that is close to the skin, if it is high, the skin temperature drop decreases. It is obvious because of the lower difference in temperature. So, it decreases the temperature difference prior to the contact, and similar that is the smaller the temperature gradient, that means less will be the heat transmission. So, that is why temperature drop it is not there. Okay. As the ambient temperature relative humidity increases, so what will happen? The difference in moisture content between the fabric and the environment decreases. So, because initially the moisture content in the fabric was high, that is why it gets evaporated. So, as the humidity in the environment increases, so it will result less evaporation. So, less evaporative heat transmission will be there. Okay. So, the fabric will the less, that means less evaporative cooling will be there, we will feel warm and humid, okay, and dampness sensation will be there. So, with the increase in ambient humidity, we will feel dampness, okay, because of less evaporation of the moisture entrapped in the microclimate. The difference between various type of fiber like cotton, polyester and wool, if it is there, it is at much higher when the ambient condition is ambient humidity is less. So, at lower humidity, so at 50-60% humidity, the difference in sensation of dampness is high in case of say polyester, cotton or wool. But when the humidity is high, say 100% relatively, it is saturated. So, that the difference in dampness sensation for cotton, polyester and wool will be negligible, because the phenomena of moisture transmission, moisture evaporation is not there, irrespective of the fiber, whether it is absorbing more or it is not absorbing. So, all the fibers, say cotton will also give dampness at high humidity, but when we are talking about the normal humidity, say 60%, 50% humidity, cotton will give better feeling, because it absorbs and it releases. Next is the another phenomena, which is clamminess. Clamminess is a feeling of discomfort, and it is related with the heat loss, and clamminess and heat loss basically it is linked with the high activity, because we feel clamminess at the high activity level. Okay. In transient humidity condition, the hygroscopic fiber can absorb or dissolve moisture from or to the surrounding environment. Okay. That is the transient condition. The hygroscopic fiber can release the moisture to the environment depending on the humidity level, or it can absorb. Okay. This can delay the moisture change in the clothing microclimate, that we have discussed. It will absorb the moisture and it will delay the moisture change in the microclimate. So, thus it delays the clamminess. So, that means if we wear a fabric made of hygroscopic fiber like cotton, and we are going to an environment which is highly humid. So, two fabrics are there, one is cotton, another is say polyester. So, cotton fabric, as it absorbs moisture, so it will keep on absorbing moisture from the environment, from the microclimate. So, it absorbs the moisture from the microclimate at least for some time. It is trying to keep the microclimate dry, irrespective of the fact that the outside humidity is high. That means, a person when he is coming from a dry humidity to high humid area, saturated humid area, he will not immediately feel clamminess, he will not immediately feel dampness. That means, it is basically it delays the process, but in case of polyester, he will immediately start feeling the clamminess. That means, it cannot delay. Okay. So, for hygroscopic fabric, it actually delays the clamminess sensation. So, he will for some time, like wool fiber, if he is wearing wool cloth made of wool, he will not immediately feel clamminess, he will take time to feel. Okay. Theoretically, this effect often acts as buffer against sudden humidity change in favor of the wearer. So, if he is suddenly going out for some time in humid area, that means it is suggested that if he is going to a hot and humid climate, he should wear a cloth made of the hygroscopic fiber. So, that at least he will not feel uncomfortable for some time. The moisture built up at the inner fabric surface facing the sweating skin is very slow in case of fabric made of hygroscopic. So, that moisture built up, that means it is that fabric is actually absorbing the moisture. So, moisture built up will be slow, and in case of polyester the moisture built up at that high humidity condition will be high. So, that means it will delay the moisture built up condition, that is it acts as buffering. Okay. Buffering from clamminess. Clamminess means when the humidity is high at that. So, there is one study where wear trial study was conducted. The temperature was kept at 28 degrees Celsius at 30% relative humidity, and the person was actually the volunteers were asked to walk on a treadmill at a certain speed, okay, and the test was conducted up to 40-minute time. Now, what we are observing, the dotted line, it is a wool, okay, and this is a polyester, this solid line is polyester, this is polyester, solid line which is a. What does it show? The clamminess sensation rating actually is high in case of polyester. The reason which we have already discussed. In comparison to wool, the polyester clothing actually the evaporation limit reaches faster, because polyester is not absorbing, it has to actually immediately release the moisture. So, that is how it is not able to absorb, really reduce the humidity in the microclimate. So, microclimate is humidity is high and the clamminess sensation is high. So, the wool garments however took up significantly more sweat than polyester garment. Correspondingly, the subject reported feeling less clammy when he is wearing wool, particularly in between 10 minute to 30 minute, where the difference is high. Okay. So, we will stop here, we will continue this discussion in the next talk. Till then, thank you.